Welcome to this video, where we will review the differences between defects and defective units and their impact on rework. We will also delve into OEE, a metric used to evaluate process performances. First, let's review the difference between defects and defective units. In this regard, several ways exist to measure defects and defective units. DPU, DPO, DPMO, and PPM are among the most common metrics. Let's review a simple example. We took a sample of 4 metallic plates from a metal mechanic process. Each should have 9 perforations made by a previous step. Important to note is that each item might have several quality characteristics, such as the length, depth, color, weight, etc. However, for practice's purposes, we will focus on just the 9 perforations made in the plate and evaluated as or defect. Black dots represent out-of-specification perforations, defects, while white dots are OK perforations. DPU stands for defects per unit. That is the average number of defects that a unit has. DPU is estimated by dividing the total number of errors by the total number of production units. In our example, the 4 units have 2, 3, 0, and 1 defects respectively. Therefore, 1.5 DPU. In other words, based on the sample taken, each unit produced has 1.5 defects on average. DPO stands for defects per opportunity. It is the average number of defects per opportunity, depending on the number of opportunities for failure. DPO is estimated by dividing the number of errors by the number of opportunities for a defect. Alternatively, DPO is calculated by dividing the DPU by the number of opportunities for a defect per unit. In our example, the 4 units present 2, 3, 0, and 1 defects, respectively. That is 6 total defects out of 36 opportunities for a defect. Therefore, 0.166 DPO. Based on the sample taken, 0.1666 defects occur for each defect opportunity. An important note is that opportunity is counted only when evaluated. DPMO stands for defects per million opportunities. It represents the average number of defects that occur in 1 million failure opportunities. DPMO is obtained by multiplying the DPO by 1 million. Alternatively, DPMO is calculated by dividing the product of DPU times 1 million by the number of opportunities for defect in a unit. In our example, the 4 units present 2, 3, 0, and 1 defects. That is 6 total defects out of 9 opportunities for defect per unit, which gives us 166,666 DPMO, or 166,666 defects per million opportunities. In other words, based on the sample, if we process 1 million of perforations on the plates, there might be up to 166,666 defects. PPM stands for parts per million. It represents the number of defective items that occur in a million units. PPM is obtained by multiplying the number of defective units in the sample by 1 million, and then dividing the product by the total number of produced units, that is, the sample size. In our example, the 4 units present 2, 3, 0, and 1 defects. That is, 3 defective units out of 4 units in the sample. Therefore, 3 defective units times 1 million, and then divided by the sample size, which is 4 units, gives us 750,000 ppm. In other words, based on the sample, if we process 1 million units, there might be up to 750,000 parts per million. Now, let's move into performance metrics related to defects in the process. First pass yield measures the final produced units without defects at the end of the process. We divide the quality units by the total units produced to obtain this metric. Here, quality units refer to those units without defects. Suppose we have a process consisting of 8 steps, from E1 to E8. 100 units go to the initial step, while 95 OK items go to the final step. Thus, 95 quality units divided by the 100 units give us a 0.95, or 95% first pass yield. Note that first pass yield does not consider the number of defects that occur in the process, only at the final stage. Therefore, this yield helps us identify the hidden factories where rework activities are conducted. Throughput yield, TPY, is a crucial metric in evaluating process performance. It represents the number of acceptable units at the end of a process, divided by the number of starting units, excluding scrap and rework. This metric gives us information regarding the actual performance of each step along the whole process. The number of quality units without defect and rework is divided by the total number of units processed to obtain the TPY. Then, this proportion is multiplied by 100 to obtain a percentage. Alternatively, the number of defective units is divided by 100, then subtracted to 1, and then the proportion is multiplied by 100 to obtain a percentage. It can be seen that step 2, E2, presented 2 defects out of 100 units. Thus, its TPY is 98%. Correspondingly, step 5, E5, has a TPY of 99%, and step 7, E7, has a TPY of 95%. It is important to note that the remaining steps did not present defects. Thus, its TPY is 100%, and those values are usually not highlighted. Rolled throughput yield, RTY, is the probability of a product or service completing the entire process without having a single defect. RTY focuses on the capacity of each process stage and not just the final results. In our example, the yield of step 2 is 0.98, or 98%. The yield of step 5 is 0.99. The yield of step 7 is 0.95. And the yield of the test at the end of the process is 0.95. The rest of the steps had no defects. Thus, its yield is 1 or 100%. The rolled throughput yield is obtained by multiplying the yields of the steps. In this case, this gives us 0.876 or 87.6%. Alternatively, the rolled throughput yield equals E at the power of negative D divided by U, where D is the number of total defects, which is 13, and U represents the total units produced, which is 100. Unlike yield as an index, RTY presents a statistically significant correlation with quality, cycle time, and costs. Therefore, it is more informative. At this point, it is essential to state that to improve a process, it is vital to have a baseline performance to compare. Remember, if you cannot measure it, you cannot improve it. Now, let's dive deep into the concept and implications of rework. Rework in the current manufacturing process affects quality and flow. Rework is understood as repeating or correcting a process to repair a defect. In some processes, the operator conducts rework in each station or step, while in others, rework is done in a special station dedicated to reworking. Consider the simple example of manufacturing a skateboard. The first step, assembly, lasts 5 minutes per board. Sanding, the next step, lasts 4 minutes per board. Finally, painting lasts 6 minutes per board. The painting step is the bottleneck, meaning that the entire process is limited to its capacity of 10 flow units per hour. If demand changes, let's say it equals 8 skateboards per hour, the painting will now have enough capacity to meet this new demand. Thus, its resource utilization drops from 100% to 80%. This artificial improvement in utilization is due to the change in customer demand, which is an external factor. But how will rework impact this? Internal defect rates impact the workload of the internal factory. If a defect is generated at one step, then the upstream units are working to produce defective parts. If corrected, the upstream processes will have a smaller workload per good output. If an inspection test is implemented before a bottleneck, then this will create more capacity on the bottleneck step. Continuing with the example and assuming that the demand is 8 boards per hour, now, let's say that the process currently has a poor quality rate of 62.5%. That means that the defect rate is 37.5%. Therefore, the rate of parts needing rework in the first step, assembly, will be 3 boards per hour. Conversely, the rate of good parts is 62.5% of the 8 boards processed per hour, that is, 5 boards per hour. In summary, 37.5% of parts need to be reworked. If this process has a rework station and the average rework per board is 15 minutes, the capacity of this rework station will be up to 4 boards per hour. Now you can see that the resource utilization per step is 67% for assembly, 33% for sanding, 50% for painting, and 75% for rework respectively. Considering a rework station with a capacity of up to 4 boards per hour might give a false impression that the whole process is capable. However, this is not true. Any change in demand will also affect the capacity of the steps, including the rework station. Let's see how the change in demand affects this process, mainly due to the rework station. Demand is equivalent to 10 2/3 of boards per hour. The rate of parts needing rework will be 4 boards per hour. That is 37.5% of the 10 2/3 of boards per hour. Conversely, the rate of good parts will be 6 2/3 of boards per hour, which is 62.5% of the demand. 4 defective boards per hour equal the rework station's capacity. Thus, the rework station is now a bottleneck. This is confirmed when we review the resource utilization per step. Now assembly has 89%, 44% for sanding, 67% for painting, and 100% for rework. In summary, defects significantly impact the flow of the process. Fewer defects improve the flow rate because we are not wasting time producing defective units, allowing us to meet the demand. A better flow rate allows us to achieve a just-in-time performance using a pull process. Now it is time to review the overall equipment effectiveness, OEE, an important metric of process performance related to defects. The overall equipment effectiveness is a key metric and tool to manage equipment-intensive production processes. The OEE is also a measure of system productivity. It gives us information about how available a process is, how fast a process is, and the quality level to produce defect-free parts. To calculate the OEE, we multiply the availability rate by the performance rate by the quality rate. The availability rate is obtained by dividing the available runtime by the scheduled runtime. The performance rate is calculated by dividing the used runtime by the available runtime. Finally, we divide the effective runtime by the used runtime to obtain the quality rate. It is important to review the 6 main groups of OEE losses to understand the 3 elements that determine overall equipment effectiveness. The availability rate might be affected by breakdowns or machine failures, which limit the available runtime. Similarly, long setup times or changeovers also affect the available runtime. The performance rate might be impacted by 2 main losses: stoppages of the machine or production line, or to work with a reduced operating speed. Regarding the quality rate, this is affected by considerable levels of rework and scrap. In addition, startup yield losses have also a negative impact. To illustrate the calculation of the OEE, let's go over a simple example. A machine's total operating time is 880 minutes per day. However, on average, there are 120 minutes of planned non-production time and 80 minutes of unscheduled time. Thus, the scheduled runtime is only 680 minutes, which is 23% less than the original operating time. To obtain the availability rate, we divide the available runtime, 550 minutes, by the scheduled runtime, 680 minutes, resulting in 0.81 or 81%. Continuing with the performance rate, we observe that the machine presented, on average, 490 minutes of used runtime from the 550 minutes of available runtime. Therefore, the resulting performance rate is 0.89 or 89%. The quality rate is calculated by dividing the effective runtime by the used runtime. In our example, a daily average of 440 minutes was considered effective production time, or effective runtime. That is, the time of producing units without defects. The used runtime was 490 minutes on average per day. Thus, the difference, 50 minutes, is the time dedicated to producing units that are out of specification. The resulting quality rate is 0.90 or 90%. This figure shows the results of the availability rate, performance rate, and quality rate, respectively. It also depicts the original operating time and subsequent times due to downtime, speed, and defect losses. The OEE is obtained by multiplying these three values, resulting in an OEE of 0.65 or 65%. In general, values of OEE larger than 85% are desired, meaning that the process or machine performs at a world-class level. Values of OEE below 85% or near 65% denote a need for improvement, while OEE below 50% indicates processes or machines that are considered laggards. To improve the availability rate, we must reduce losses related to machine failures and setup times. The following are some points in this regard. Let operators undertake their simple maintenance tasks. Conduct planned maintenance, both preventive and predictive maintenance. Undertake focused equipment and process improvement. Employ SMD to shorten setup time. To improve the performance rate, we must diminish losses related to stoppages and reduced operating speed. The following are some recommendations. Track production performance, for example, hour-by-hour charts. Conduct root cause problem solving to determine whether the problem is due to staff, material, method, or machine. Develop standards to make sure maximum utilization of machines can be reached. Finally, to improve the quality rate, we have to reduce or eliminate defects that lead to rework or scrap, and also reduce startup and yield losses. Two recommendations are: implementing standard procedures to secure the constant quality of processes, and implementing quality checks at the right positions within the process to eliminate the need for rework. In summary, the OEE metric is significant for lean production. OEE is a straightforward metric that combines meaningful measures of equipment availability, performance, and quality. OEE data can be collected and monitored simply, manually, or with a standalone or integrated IT system. OEE enables systematic and detailed waste monitoring, including wasted time and defects. It captures small losses that accumulate to significant losses over time. The following are some references and recommended readings. Thank you.